So my name is Peter Dayan. I'm the director of the Max Planck Institute for Biological Cybernetics and a professor at the University of Tübingen in Germany. So my connection to Edinburgh is I was a graduate student here with David Wilshaw and David Wallace. So when I was here, I already started working on the area that I then have carried on working for the rest of my career, which is kind of a bit embarrassing in a way. And then I work in the general area of neural reinforcement learning. So I'm interested in how it is that we do both effective and defective decision making, both in humans and in animals. So there's a really wonderful wealth of work from many disciplines, from operations research, from economics, from control theory, from engineering, and also from psychology, about what it is, what defines a good decision, essentially. And so there you'll want to say, what are the states of the world, so how the world varies, what are the utilities or rewards or punishments that might happen for the actions that you take. And then from those pieces, what you want to do is to piece together, well, okay, what action should I take given what I'm uncertain about or given what I know about? Some of the things you might want to do is to collect more information to make a better decision. So often we're in circumstances where when you make a decision now, it doesn't have an immediate impact, but has an impact later on. You want to work out, well, what should I do now in order to make that work well in the future? So from all these bodies of work, they all have their ideas and also mathematical methods, essentially, for defining what it is to make a good decision. And of course, animals have had to make good, and actually even plants and other biological entities have had to make good decisions as well. Because if they didn't make good choices, they wouldn't survive to tell the tale. And so both we can say, well, from what we might think of as a normative or a computational perspective, we have a really good idea of what these good decisions are. We have this wealth of work in psychology about what sorts of decisions we and other animals actually make. And then we now also work quite a lot on the neuroscience, the neural substrates of these decision makings. So to give you one example, one of the things that I'm very interested in is reward processing, because of course a lot of the decisions we make are influenced by the rewards that accrue based on those decisions. And so again, we know quite a bit from all those bodies of work that I talked about what rewards, how we can link the rewards that we might get to the actions that we choose. And then we know a lot about the psychology of it. And then the neural substrates of reward processing relate to both what you might think of as sort of evolutionary primitive, preserved structures, which are interested in monitoring how we receive rewards, how we make predictions about future rewards we might receive based on the actions we take. And then other more evolutionary modern structures involved in trying to work out what the states of the world are, which influence what the rewards might be, how they may relate to the actions that we have, then help us choose actions which in general should be good. So that's the effective decision-making side, where we know quite a lot about what we should do. And then, of course, then humans are notoriously not perfect decision makers, myself included. And so then we're interested in what are the different sorts of errors that humans can make? Where do they come from? How do they change in the context? How do we learn perhaps to be better, or in some cases learn to be worse decision makers? And then on the context of diseases, like particularly psychiatric diseases, where people make decisions that either they, in other circumstances, or society wish they didn't make, we'd like to understand more about the neural basis and the psychological basis of those decisions, which are then unfortunate decisions, and see, well, what could it be? What could the structure of those deficiencies be, of that dysfunction be? And then even potentially, how is it that we might imagine therapies to work or to ameliorate some of the symptoms? So there are many challenges. One of the really exciting things, if I might sort of say, essentially we had a challenge because of the availability of data, is that experimental methods in this field have changed really dramatically over the last few years. And so neuroscience is a very active area of research, and there's just a huge wealth of new techniques that come out, which means that we can essentially ask questions that we have wanted to ask for 30 years and we're really unable to ask. So in my particular case, some of the structures that are involved in these aspects, for instance, reward processing, are particular neural chemicals which are called neuromodulators. So one of them, example, is dopamine, which is a neuromodulator, which is therefore a substance which is projected quite widely in many areas of the brain, particularly into the areas involved in systems involved in making predictions, and also in some sense in choosing and learning to choose actions. And so for a long time, it's very hard to measure dopamine in the brain in a very accurate, temporally and spatially faithful way. And now there are much better ways of doing so based on advances in optogenetics. And I also have collaborations with a group around Reed Montague, who's in Virginia Tech in America, who's interested in trying to record levels of dopamine in human brains. These are patients who've given us permission, under very strict ethical considerations, to record levels of neuromodulators like dopamine whilst they're during, for instance, implantation for deep brain stimulation, so psychosurgery essentially, or neurological surgery for neurological interventions, and then also during epilepsy monitoring. And so that then allows us to ask a set of questions again we could never have asked before. So really those data, of course, present enormous challenges, but they're also very exciting to us, but allow us to really get with much higher fidelity to ask those sorts of questions. So in the context of psychiatry, of course, there are very, very many challenges. It's a very complicated discipline, and it's one can enumerate a huge range of challenges that come there. One example, for instance, is that the whole definition of diseases in psychiatry is something which is under sort of constant, not attack, but certainly under constant debate. And so therefore, for instance, if you wanted to understand something about the course of one of those diseases, to the extent those diseases are not themselves sort of neatly encapsulated phenomena, but really more like sort of latent structures encompassing a bunch of symptoms that come together. That means that the underlying deficits or dysfunctions that might happen for people with the same nominal disease could be very different. And so what we're trying to do is to work out what some of those underlying dysfunctions might be. But of course, that's very difficult if you don't start with a sort of agreed or agreeable definition of the disease itself. So we have challenges and opportunities in all these different areas. Yeah, so why might dopamine be anybody's favorite neuromodulator? In fact, it's the only neuromodulator I know that has a film with the title dopamine. So the other ones haven't risen to that level of a fame yet. So I started working on dopamine actually just after I was a student here. I did a postdoc in San Diego with Terry Sinosky, and there, together with Reed, we started working on thinking about dopamine. And it's my favorite neuromodulator because it's associated, as far as we can tell, with positive reinforcement. So dopamine, levels of dopamine or activity of dopamine neurons, at least many of them, not all of them, but many of them, respond when you make what's called a particular sort of what's called prediction error. So if you want to have a system which is learning predictions, the best possible signal you could have is a prediction error. What's the difference between what actually happens and what you predicted would happen in the first place? So in this case, what actually happens is to do with something about the reward value of what happened, and your prediction is a prediction of what that reward value should have been in the first place. And so it looks as if dopamine is a very particular sort of prediction error for that difference, that discrepancy I just talked about. And that is the right signal, it turns out, both for learning predictions, which is kind of obvious, but it also turns out, for a very interesting reason, to be the right signal for learning actions too. It turns out that when you get more, by doing an action, you get more reward than you expected. That means you have a positive prediction error. Then that's a really good action to try again if you're in the same circumstance. So as you can imagine, a neuromodulator which is involved in positive reinforcement is going to be a nice sort of neuromodulator to work on. You might wonder, are there neuromodulators which are involved in the opposite, negative reinforcement? And the other neuromodulators also have their own very important computational roles to play, but none of them is quite as nice as dopamine. So dopamine, the activity of dopamine neurons and then the release of dopamine, or at least many dopamine neurons, has a very particular temporal structure, which is really ideally designed to help us solve, or seems to be ideally designed to help us solve a very particular problem, which is how do we learn in the long run rather than the short run. So to give you an example, imagine that you do an action now which turns on a light, but the turning on the light implies that you're going to get a reward at some later point in the future. So you'd like to say, well, doing that action was a good action because it led to a consequence, in this case, turning on a light. And that light turned out to be good because you've been able to learn the fact that the light then predicts this future reward. So it turns out the dynamics, the way that dopamine responds is ideally designed to help us learn this sort of almost like this chain of predictions and then actions associated with those predictions. So let me try and explain that a little bit. So I told you before that dopamine is responding to a prediction error. So what's different between what actually happens and what you predicted happened. So in the case you get an immediate reward, so you get a drop of juice in your mouth, for instance, then it's very easy to imagine what the actual outcome was. It's just a drop of juice in the mouth itself. But since the most interesting aspect of prediction is prediction about the future, something that happens not now, but is going to happen in the future. We would like to have a signal which helps us learn what those predictions are, whether future predictions rather than at the moment. So imagine we have this case that I talked about where the light predicts a future reward. We can ask, what would we like to predict? And what would the right prediction error signal look like in that case? So I argue that what we'd like to predict is that when the light comes on, before the light was there, we predicted there was no reward, there was no prediction. When the light comes on, we'd like to make a prediction that there's going to be a reward in the future. That prediction remains constant during the time we're waiting for the reward. Then as the reward comes, that prediction goes back to zero. You've now sort of requited that prediction with the reward you actually get. So if that's what the prediction should look like, at the end point of learning, is there a prediction error at all? And if so, what does it look like? Well, at the time of the reward, there's no prediction error. It was perfectly predicted. By the time you've learned how to predict the reward, you know it. Whilst you're waiting for the reward, there's no prediction error because you're just in this state of grace waiting for the prediction waiting for the reward to come. So the only prediction error that happens is at the time of the light itself, because before the light came on, you didn't know the light was going to come on, but now the light comes on, you know you're expecting the reward in the future. So it turns out that many or most dopamine cells actually fire at the time of that light, the time when you're expecting this, the first time you know that you're expecting this future reward. So that's the activity we get in the dopamine cells at the time of the light, even at the end point of learning. Now, why is that good? Well, remember what I told you, the structure of decision-making here was that we do an action which might turn on this light, which predicts a reward, or maybe a different action turns on a different light, which does not predict the reward. So now when I do the action and that turns on the light, by looking at the dopamine activity, I see a peak in activity then, and that can act to reinforce the action that I did. So in the same way that I did an action and I got an immediate reward, that I actually got the drop of juice in my mouth, I can say, well, now I need to have a reinforcement that says, now make it more likely to stamp in that action, make it more likely I do that action in the future. Then that's something I can easily do. But now when I just take that action, and I just get the light get switched on, now that dopamine response at the time of the light, that can also reinforce the action that I just took in the same way that actually getting a real reward, a real unexpected reward could reinforce that action. So in many cases, we have to act in worlds where we don't get immediate information about the consequences of our action. So one example is, for instance, take a game of something like chess, where you make a move now, but you don't discover for many moves later whether it was a good move or a bad move. Maybe there was one fatal flaw that you made. Every other move you did was perfectly correct, but there was one thing that went wrong. And there's what's in the literature is called a temporal credit assignment problem. You want to assign credit or blame to an action that you took. And this dopamine signal is a way of assigning credit. So in this case, it assigned credit to the action because it led you to a state, which is the light coming on, which is predictive itself of something good happening in the future. So this positive reward you're going to get in the future. And so the dopamine, the structure of dopamine, this temporal difference prediction error invented by Rich Sutton and Andy Bartow, which relates to this engineering field called dynamic programming, or operations research field called dynamic programming, then is what allows us to make choices now which have really good consequences over the long run. The question was, if then we know that the dopamine then responds to the light, once you then reliably do an action, which then leads you to this light, do we not then expect the activity of the dopamine at the time of the light to disappear, and activity at the time of the action, the preceding action, or the state which led to the action in the first place, also to cause the response of dopamine? That actually turns out to be a really complicated and interesting question. In fact, I'm doing quite some research on at the moment, which is really the coupling between almost like motivational forces, like how vigorously, for instance, do you choose to press the action? It might relate, for instance, how much reward you're going to get, and whether that is also influenced by the dopamine, which is then released associated with this sort of prediction of the action. So one issue is that the reason you did an action is maybe there was some preceding states, for instance, like the case of chess, like a board position, which inspired you to do that action in the first place, to move your pawn one way or the other way. And so then, of course, that state would also gain a value by itself. And there could be also, as you can imagine, a sort of chain of dopamine responses associated with that. And that actually turns out to be true. But one of the things I talked about yesterday also is the fact that dopamine seems to be not only associated with learning about affect, so affective values, so reward valences, but also associated with effect, associated with actions. And so it turns out that people and animals as well will tend to engage enthusiastically and vigorously with states like light, for instance, which predict positive outcomes, like the light predicting the food we had ourselves. And so, indeed, aspects of that action will be encouraged by by a dopamine response that might happen before that action, inspiring the action. So this leads to a number of complexities. So first, task complexities, when we set up an orthogonalization between what action you should do or whether you should do an action at all and the prediction of the value associated with that. And that's one area of active research that we might have. And then there are other cases where we wonder about the sort of temporal profile of dopamine. For instance, is the brain making successive predictions that it's about to do an action? So there are areas where you see a sort of ramping profile of dopamine responses towards action. So before an action happens, you see the dopamine signal rising on the way towards on the way towards an action. And so understanding the way that interacts with the other aspects of dopamine to do with learning and is actually, as I mentioned, quite an interesting area of research at the moment. Also, different structures which receive dopamine signals may operate in slightly different ways with respect to this, and that's something else that we in the field are looking at. And one thing to point out is that one of the major diseases which involves dopamine is Parkinson's disease, where you see a progressive cell death of the dopamine cells. And one of the symptoms in Parkinson's disease is bradykinesia, which is very slow action. So people are very slow speech, also slow actions as well. And so that may partly relate to this death of these dopamine cells along the way. So in some sense, the most unexpected aspect of my career path was really a choice I made before I came to Edinburgh in the first place. So I had been sponsored by British Telecom, as an undergraduate at university where I read maths. And I'd been working for them for a couple of years. And I had one of these strange career choices where I could have done an MBA or I could have done a PhD. So I had this PhD offer to come to Edinburgh at the time, Buccleuch Place, or do an MBA at the London Business School. It's one of these cases where I work on decision making, and it's a case where decision making under extreme uncertainty. I didn't know what it would be like to have a PhD. I obviously didn't know what it would be like to have an MBA as well. And so it was a very odd choice where I thought, okay, it was going to make a huge difference what I do, but I simply don't have enough information to really decide which would be the best choice to do. So the best I could hope for is that I thought it'd be easier to do a PhD first and an MBA second than an MBA first and a PhD second. So I went for the PhD, and then essentially that has sort of defined, in some sense, the rest of my career. And I obviously never went back to doing that MBA. So apart from that, I've been extremely lucky. When I was a graduate student here with the Davids, David Wilshaw, David Wallace, I went to a summer school. So at the time, the area we worked in, connectionism, sort of barely existed in any program. You couldn't do a course in it. I'm really envious of my students. They can now do real courses in the areas which we could only sort of, computational neuroscience, same thing. We could only sort of glean from the literature ourselves at the time. But that a number of people, particularly Terry Sinosky and Jeff Hinton, had set up this thing called the Connectionist Model Summer School, which in 1990 took place in San Diego. And so I went there when I was halfway through my graduate studies. And so there, I both met a whole bunch of the investigators who I now interact with. They became the people who helped define the field, and also met a whole bunch of other people who I didn't really have exposure to in Edinburgh. As a result of that, I actually then did my two postdocs, one in San Diego with Terry, and then one in Toronto with Jeff Hinton. And then I was lucky; I got a job at MIT as an assistant professor. Then I came back to Britain in 1998 to help found the Gatsby Computational Neuroscience Unit in London. So I then stayed there for 20 years or so, and then I went to Tübingen in 2018, where I've been for 5 years. And what's really impressive in Edinburgh is, so when I was here, there were really these sort of separate structures. We had the Centre for Cognitive Science in Buccleuch Place. I was actually formerly a graduate student in the physics department, because that's where David Wallace was. And then it was even before the ANC, so this one of the institutes inside informatics has been formed. And so it was clear there was a lot of incredible excellence here. There was AI, a very long storied history of AI in Edinburgh, right, dating back indeed to where this department was founded with people like Donald Mickey. But people weren't quite interacting together in quite that way. And so it's been really wonderful to see the formation of the informatics, the formation of all these different people coming together. And now this really huge and powerful institution, really one of the best places in the UK to study and do research in this general area of informatics and of course with AI and machine learning. So I think there are just many, a huge number of opportunities that the department has, or the school has, in these areas. And the fact that you can have these institutes, you can have people working together, I think is excellent. And so it's been a pleasure as an alumnus to come back and have a look and see how things have evolved in these ways over the time. Of course, there was a sort of pleasure to the sort of bespoke way that we ran things in the days of the Clue Place, up in these these small flats overlooking the meadows, which was also very nice. And I think that's a little bit lost now. All you do is look over the Appleton Tower. But it's a great pleasure to see how it's developed and to maintain some links with the institution afterwards.